In Chemical Equilibrium 1, we're going to discuss dynamic equilibrium. Now, chemical equilibrium is defined as a state in which the forward rate of a chemical reaction is equal to the reverse rate. Dynamic implies changing, fluctuations, and that's exactly what is occurring in dynamic equilibrium. Now, equilibrium is denoted with the following symbol. Let's look at a chemical reaction in dynamic equilibrium. Here we have nitrogen dioxide gas yields dinitrogen tetroxide. Each reactant is being reformed by the reverse reaction, and this is occurring at the same rate that it is being consumed by the forward reaction. So when we say forward, we mean to the right. So in this example here, the forward reaction is producing the dinitrogen tetroxide. Now, it's very important to make this distinction that the rate at which a given species is being consumed or produced is completely dependent on the molar ratios from a balanced chemical equation. In other words, it depends on the coefficients. So in our example reaction here, for every 2 moles of nitrogen dioxide gas that is consumed, 1 mole of dinitrogen tetroxide is produced in the forward reaction. Let's look at this schematic to help understand dynamic equilibrium. This represents the initial reaction before any products whatsoever have been formed. The blue circles represent moles, so note that we are starting with 8 moles of reactants. As the reaction proceeds, we have reactants moving to the right and forming products. This is in the forward reaction to the right. Again, note the total number of moles. Now we have 7 moles on the right and 1 mole on the left. However, the reaction then pushes back to the left, and it's in the reverse reaction reforming the reactants. And in this case here now, we have 5 moles of reactants on the left side, and we have 3 moles of reactants or products on the right side. And in dynamic equilibrium, we reach the state in which the concentration, which is underlined, this is critical, the concentration of the products and the reactants remains constant. In our schematic, our constant concentration is going to be 2 moles of the reactants and 6 moles of the products. That is in dynamic equilibrium. Let's go ahead and do a practice problem. Nitrogen dioxide is being consumed at a rate of 0.031 moles per second. That's the rate. And it is in equilibrium. How many moles of dinitrogen tetroxide are being consumed each second? All right. So ostensibly, it's like, wait a minute, nitrogen dioxide is being consumed, and then how many moles of dinitrogen tetroxide are being consumed? So we need to look at the fact that our concentrations are going to remain constant at dynamic equilibrium. However, this question is saying that if the forward reaction in which nitrogen dioxide are being consumed, moving to the right, as the reactants push back to the left, the dinitrogen tetroxide are being consumed in the reverse reaction. So what we need to do is write down what we know. Then we're going to use dimensional analysis to try to convert this into the rate that the dinitrogen tetroxide is being consumed. The key is going to be these molar ratios here, and so 2 to 1. So one way to think about this is the nitrogen dioxide is being consumed at twice the rate that the dinitrogen tetroxide is being formed. That's one way to think about this, and that's exactly what we're looking at here. So we end up with our final answer. It's exactly half the rate. So it's somewhat intuitive, but this idea of reversible reactions and equilibrium is oftentimes confusing to students. So this is just a recall here, that the rate at which a given species is consumed and or produced is dependent on these Molar ratios, these coefficients. Graphically, we can look at this. The red represents the forward rate. The blue is the reverse rate. Please think about this for a moment. In the forward rate, remember our schematic. We started with everything pushing to the right, so we had a very high rate. As the reactants were turning into products in the forward reaction, they are producing the products. So now we start to see the formation of products in the reverse. Okay? Because the reverse, as products are formed and dynamic, as it approaches dynamic equilibrium, the reverse process is occurring. And then the forward process until equilibrium is achieved. And at this case, equilibrium is achieved when the forward and reverse rates are the same. Now we can look at the amounts as a function of time. This is the concentrations. And once dynamic equilibrium has been achieved, the concentrations of the products and reactants is constant. So graphically, if we look at concentration over time, amount over time, we see here as the reactants are being consumed, products are being produced, the products increase in concentration, the reactants decrease in concentration. And once equilibrium has been achieved, there's no change in the amounts. So at equilibrium, there is a higher concentration of products in this graph than there are reactants. However, their concentrations respectively will remain constant. Our Georgia Standards of Excellence are looking at principles to manipulate factors that will affect chemical reactions. So looking at changes in concentration, temperature, and pressure on a chemical system and how that will lead to a shift in the forward and or reverse reactions. I'll see you guys in class.